Welcome to 5.5. Today we're going to be setting up triple integrals in cylindrical and spherical coordinates. So let's just jump right in to this example here where we want the volume of the region bounded above by a sphere and on the sides by a cylinder. And we're going to use cylindrical coordinates for this. So first of all, the volume is going to be the triple integral over the region of the volume element. And in spherical coordinates, the volume element is r dz dr d theta. Okay, now let's get our limits on z. Z, if we imagine straight lines going upward like this, z starts at 0 and it leaves on the top cap of that sphere. And so let's go over here and solve this equation for z. First of all, we want to use cylindrical coordinates. So x squared plus y squared is r squared. So we have r squared plus z squared equals 25. And so z is going to be positive the square root of 25 minus r squared. So that's our upper limit up here on the triple integral. Okay, for the limits on r and theta, we're told that the cylinder is x squared plus y squared equals 4. So in the r theta plane, that's a circle of radius 2. So r is going to go from 0 to 2, and we want to go all the way around, so theta goes 0 to 2 pi. Okay, and then to actually evaluate that integral, it's a triple integral, so you'll need 3 separate integrals, and I did that here. You can read through it, but I'm more interested today in the setups because I think that's the more challenging part. Okay, second one, again, I did the integrations. You should double check my work, but let's just work on the setup. Volume is equal to the triple integral of the volume element, but in spherical coordinates, the volume element is rho squared sine phi d rho d phi d theta. So we want the limits on rho first. Rho is the distance from the origin. So if we think of rays emanating out from the origin, they're inside the region right from the get-go at rho equals 0, and they leave the region on this sphere rho equals 2. So they're going to go from 0 to 2. Then we want to work on our limits on phi. When we're talking about these rays from the origin, they're not in the region up here at phi equals 0, the positive z-axis. In fact, they don't hit the region until right there, the edge of that cone, which is phi equal pi over 3. So our starting limit on phi is pi over 3, and our ending limit is in the xy plane, that's phi equal pi over 2. And again, theta is going to go from 0 to 2 pi because we want to go all the way around. Okay, now we're going to do some volume setups. Let's set up the volume for the top cap here, starting with rectangular coordinates. So the sphere in rectangular coordinates, it's a ball of radius 4. So that's x squared plus y squared plus z squared equals 16. Now we want the top of that sphere, so I know I'm going to need z in a minute. So if I just solve for z, I get positive square root of 16 minus x squared minus y squared. Okay. For the region of integration in the xy plane, I need to determine where the plane meets the surface. So what I'm going to do is just take this z here, 2 root 3, and plug it in to this equation here. So I get x squared plus y squared plus 2 root 3 squared is 12, and that equals 16. So x squared plus y squared equals 4. That's a circle of radius 2. Okay, so now we're ready to start our limits. If we think of vertical lines going through that region, they're going to start at the plane z equals 2 root 3, and they're going to leave on the sphere cap 16 minus x squared minus y squared. Now y is next, so we come over here to our xy picture, think vertical lines. Y, the lower half of this circle, is negative the square root of 4 minus x squared. And the upper half of this circle is positive the square root of 4 minus x squared. It's a little bit crowded there, sorry. And then limits on x are negative 2 to 2. All right, now for cylindrical, we don't have to make too many changes. Z is going to go from 2 root 3, again to the top of the sphere, and the only thing I have to do differently for this limit is change the negative x squared minus y squared to negative r squared, because we can't have x's and y's in the cylindrical coordinates. So we need to write everything in terms of r and theta. Okay, and that circle above of radius 2 is just r equal 2. So r is going to go from 0 to 2, and theta is going to go from 0 to 2 pi because we want to go all the way around. Okay, now for the spherical coordinates, The sphere is a ball of radius 4, so that's rho equal 4, and the plane is z equal 2 root 3. And in spherical coordinates, z is rho cosine phi. So if we solve that for rho, we get rho equals 2 root 3 secant phi. So over here, the plane is rho equals 2 root 3 secant phi. Now, where do these surfaces meet? I'm going to set rho equal to rho. So 2 root 3 secant phi is 4. So secant phi is 2 over root 3. Take the reciprocal of both sides. Cosine phi is root 3 over 2. So phi is pi over 6. Okay, and now we're ready to start putting our limits of integration on. Now imagine a ray starting at the origin and emanating out. That ray is going to hit the region at the plane, which is 2 root 3 secant phi. These are the limits on rho, and it leaves at rho equal 4. The phi limits, you're right in the region at phi equals 0, and you go to, we determine phi equal pi over 6. And then you leave the region, and we want to go all the way around 0 to 2 pi. So those are the limits in spherical coordinates. All right, last one, we want to set up 3 integrals for the volume of this ice cream cone here. For the rectangular coordinates, we want to think vertical lines first. Those will be the limits on z. So z enters at the cone, which is the square root of x squared plus y squared. And it leaves on the top of that sphere, which is the square root of 4 minus x squared minus y squared. Now, to determine the xy limits, we need to find out where these two surfaces meet. So what I'm going to do is set z squared equal to z squared rather than z equal to z. So if I set z squared equal to z squared, I get 4 minus x squared minus y squared equals x squared plus y squared. Now you can clean that up to get x squared plus y squared equal 2. So that's a circle of radius root 2. So that tells us our y coordinates are going to be negative the square root of 2 minus x squared to positive the square root of 2 minus x squared. And our x coordinates are going to be negative root 2 to root 2. Okay, for cylindrical, this is pretty easy. The z coordinates are going to be the cone in cylindrical coordinates is z equals r. So this is just going to go from r to the square root of 4 minus r squared. And for our r theta limits, we want to think of that circle in terms of polar. That's a circle defined by r equals root 2. So r is going to go from 0 to root 2. Theta goes from 0 to 2 pi. For spherical coordinates, we know the sphere is rho equal 2. Now, for the cone, we want to use the fact that tangent phi is r over z. But in this case, on the cone, r equals z, or z equals r. So tangent phi is 1. So the cone is defined by phi equal pi over 4. So this one's pretty easy. Our limits on rho starts at the origin and it goes to 2. And then phi is going to go from 0, because we're inside the ice cream cone at phi equals 0, and we stay inside until we hit the edge of that cone. So we're going to go from 0 to pi over 4, and then again, all the way around 0 to 2 pi. Okay, and that's it. And you can see that the most challenging part is the setup. And that is the end of this section.